How many numbers would you need to describe the Moon? To begin with, it is pockmarked with a wide variety of craters from different asteroid impacts over billions of years. A similar exo-moon orbiting a similar exo-Earth in a different solar system, even if superficially alike, would have a completely different pattern of asteroid impacts. To characterize each precisely at a minimum, we would need to give two coordinates, longitude and latitude, for every one of the thousands of craters, along with the size of each crater. Very rapidly, we find ourselves needing thousands of numbers to describe a moon, even before we start talking about the chemical composition of the moon's surface and how that varies in different regions. The number of numbers we need quickly expands from thousands to millions and beyond. And that is just a moon, one of the comparatively more simple objects in the cosmos. How many more numbers would it take to describe a planet, a star, a nebula? Or indeed, how many numbers would it take to describe the most massive single object in the entire universe, a black hole? The answer for these monsters may surprise you. 3. 3 numbers and no more. No matter how heavy they are, no matter where they were formed, no matter whether they are in our own Milky Way galaxy or a billion light years away, 3 numbers and only 3 are sufficient to define them completely. On the one hand, this makes black holes seem like very simple objects. Only 3 parameters are necessary to classify them: their mass, electric charge, and angular momentum. Know these 3 numbers and you have everything. And yet there are an enormous number of ways to form a black hole. They can be formed by gradually swallowing up dust and gas over billions of years. They can be formed by the direct collapse of a massive star in a Type II supernova. Perhaps yet another could grow through repeated mergers of other black hole pairs. We can even imagine a hypothetical black hole formed from the contents of every encyclopedia and electronic data bank of every civilization in the universe, every piece of information, and every single number ever thought or said by anyone ever. Anything and everything in the universe can go into a black hole, and yet once it is formed, all of that information is reduced to 3 numbers. How the black hole was made and what went into it becomes almost irrelevant. And so the question is, given this almost uncountably large number of possibilities for making a black hole, how can they then be described by just 3 numbers? Where has all the other information gone? Has the black hole forgotten about its origins, or does this information survive in some hidden form? Just what is inside a black hole? And what could it mean for the rest of the universe? Where are you really from? Many of the atoms that make up who you are can actually be traced back to the very first second of the Big Bang, 13.8 billion years ago. It is fascinating to trace our origins. And that's why MyHeritage is such a fun service to sign up for, our sponsor today. MyHeritage makes it fun and easy to build your family tree and discover your origins, and you might also find new relatives. My family is a mix from all across the British Isles, but I was still surprised, for as soon as I typed in my father and mother's name and birth dates into their amazing smart match system, it connected my family tree with someone in Australia, which revealed waves of relatives I never even knew about. So within 5 seconds of logging on, my family tree already had 72 people. And as well as this, I matched with someone on my father's side that opened up whole new branches of cousins in the US. My family was more widespread than I thought. And this was possible because MyHeritage is a worldwide leading family history service, and they have more than 20 billion records available. Indeed, here is an image of my great-great-grandfather I had never seen before. And as a bonus, you can even enhance and colorize old photos like these to bring your family back to life. So sign up for a 14-day free trial and enjoy all the amazing features MyHeritage has to offer. Thanks to MyHeritage for supporting educational content on YouTube. In the 1780s, the position of a country priest in the Church of England was not especially demanding. a large house with a decent income, a group of servants to do the household chores, and younger curates to take services and visit the sick. To those who wanted it, a life of lazy leisure was on offer. But to those who wanted something more, there was time to think deeply about the world around them. And this is how English parson John Michell spent his time. In the 1780s, Michell had a pretty good idea of how gravity worked. A century earlier, Isaac Newton's theory of universal gravitation had shocked the scientific world. Gravity, Newton argued, was a universal force. Anything that had mass gravitated pulled instantaneously on everything else. Nothing could avoid the force of gravity, not even, Michell mused, light itself. For, as well as thinking about gravity, Newton had also argued that light consists of tiny individual particles, little atoms of light, which we would now call photons. If this theory of light as particles were true, and gravity was universal, then gravity should be acting on these tiny particles of light, tugging at them and pulling them back. Mitchell also knew that light travelled fast, very, very fast. Indeed, earlier in the 18th century, the astronomer James Bradley had measured the speed of light and measured it well and accurately through thinking about the aberration of light from distant stars. As the Earth moves through its orbit, the vector combination of the velocity of the Earth and the velocity of light changes, just a tiny amount, but enough to change, slightly, the apparent location of stars in the sky. Through this, the speed of light was known to be around 180,000 miles per second. This was fast but not infinite. And finally, intuitively, Mitchell knew that an object thrown upwards would fall back down. But if thrown upwards fast enough, this does not happen. Instead, it has enough speed to escape the Earth's gravity and reach space. The threshold value, known as the escape velocity, is the minimal speed of vertical launch required to escape a planet's gravity and reach infinite space. It is an easy calculation in Newton's theory of gravity to work out this escape velocity for any given planet and how it depends on the size and density of the object. The more massive the object and the more dense it is, the bigger the escape velocity. For the Moon, this escape velocity is about 2.4 kilometers per second. For the Earth, this becomes about 11.2 kilometers per second. For Jupiter, just under 60 kilometers per second, and for our own Sun, roughly 617 kilometers per second. But imagine an even denser body. What, thought Michel, about a body which was sufficiently dense that its escape velocity exceeded the speed of light? For such a body, light emitted from the surface would not be able to escape. In this case, such a body would appear as gravitationally massive but entirely dark, trapping even light under the pull of its gravity. The language and argument here is that of the Newtonian physics that would be replaced by Einstein's theories, but the concept it is describing lives on and is clearly recognizable. Michel's work was, although the actual name would not be used for almost 2 centuries, the first description of what we now call a black hole. Michel was way, way ahead of his time, and his results seemed no more than an abstract curiosity. It therefore went into the scientific backdrawer and stayed there for 150 years. The next time this drawer would be opened would be in the miserable trenches of the First World War, where the German astronomer Karl Schwarzschild, desperate for an escape from the hellscape surrounding him, pondered the equations of Einstein's brand new theory of general relativity. Having developed his special theory of relativity in 1905, 10 years later Einstein succeeded in extending it to include gravity, constructing his general theory of relativity. This theory requires 10 equations to describe it. These are now familiar, but when first written down, they looked formidable and almost impossible to solve. In 1915, the ways into these equations were unknown. Trying to solve them, Schwarzschild looked for the simplest possible solution he could imagine: a spherically symmetric space-time around a concentrated point-like mass. Plugging everything in and calculating carefully, he obtained a solution. Now known as the Schwarzschild solution, this is probably the most famous solution of Einstein's equations. Schwarzschild's solution involves one parameter, a uniform spherical mass. In general relativity, mass deforms the nearby spacetime. The magnitude of this deformation depends on the radial coordinate. The closer to the mass, the bigger the deformation, while far away, there is little change. The Schwarzschild solution has one deep and striking property visible in it. As the distance from the mass comes in from infinity, there is a critical distance where something strange happens. Some terms in the solution appear to go to zero, while others go to infinity. What did this mean? Although it was not possible to go through the full mathematical derivation, these zeros and infinities at a critical radius, known as the Schwarzschild radius, indicated the presence of an event horizon for the black hole solution. A spherical shell at a certain distance from the center of the black hole that represented a point of no return for objects coming in from far away. No object can move faster than the speed of light. Outside the horizon, an object moving at the speed of light away from the black hole can escape the gravitational pull of the black hole and get to infinity. But any closer to the black hole than the event horizon, there could be no escape, not even for light. The laws of physics themselves forbade any escape. Any astronaut that crosses the black hole event horizon finds him or herself on a one-way passage towards the center of the black hole. Once inside the event horizon, time always points towards the very center of the black hole. As the astronaut falls further in, the pull of gravity becomes stronger and stronger. And so the astronaut continues falling until they reach the singularity itself, a place where the laws of classical general relativity break down and the curvature of space-time becomes formally infinite. This was similar to Mitchell's calculations of a radius where the escape velocity exceeded the speed of light. If a certain mass was condensed into a radius smaller than its Schwarzschild radius, it would collapse inescapably. The Schwarzschild radius for our Sun is about 3 kilometers, and for the Earth, it is less than a centimeter. A human's Schwarzschild radius is on the order of 10 to the power of -23. Smaller than the nucleus of an atom, and were all the stars and gas and dust within the Milky Way somehow condensed into a radius less than 0.2 light-years, a truly mammoth black hole would eventually form. Schwarzschild's solution was found in 1915, but as with Michel's work, for half a century it seemed merely an intellectual curiosity. Did it mean anything physical, or was it simply a mathematical artifact? Unfortunately, as quantum mechanics revolutionized one branch of physics after another through the 1920s, 1930s and 1940s, gravity and general relativity were viewed very much as a backwater. The comments of the American physicist Richard Feynman on a conference on gravity he attended in the early 1960s give an idea of what people thought about it. "I am not getting anything out of the meeting. I am learning nothing. Because there are no experiments, this field is not an active one, so few of the best men are doing work in it. The result is that there are hosts of dopes here, and it is not good for my blood pressure." But the state of the field, described in Feynman's caustic summary, would all change in the late 1960s, as a combination of theoretical and observational breakthroughs brought research into black holes and general relativity back with a vengeance, both observationally and theoretically. And this has remained the case to the present day. And in the public mind there is one scientist more than any other associated with this renaissance. Among the human icons of 20th century physics, Stephen Hawking holds a privileged place. His remarkable life story has inspired millions. Born in 1942, he studied undergraduate physics at Oxford before moving to Cambridge to do a PhD. But during his doctorate, Hawking's life changed drastically in two connected ways. First, at the age of 21, he was diagnosed with a degenerative muscle-wasting motor neuron disease, which had a typical life expectancy from diagnosis of around 18 months. Second, having coasted to a first-class honours degree at Oxford, for the first time in his life, he started working hard and with intensity. As the prospect of early death loomed, he threw himself into his work with a desire to achieve something and leave a legacy of his talent. Hawking would ultimately outlive others with the disease, passing away in 2018 at age 76, celebrated as one of the world's most renowned scientists. The scientific acclaim came from the first black hole renaissance, occurring between 1967 and 1974. During this period, Hawking and mathematician Roger Penrose collaborated and revitalized general relativity, producing groundbreaking theorems. They resolved the question of whether collections of heavy particles under gravitational pull would collapse into a black hole or slingshot away. Their conclusion was definitive. Under general conditions, matter would indeed collapse, leading to a singularity surrounded by a black hole. This was not just intuitive, it was a mathematical proof. The collaboration also introduced Penrose diagrams, a powerful way to visualize complex solutions to Einstein's equations. These diagrams made it easier to see the relationships between different points in space-time, clarifying causality and defining horizons as regions cut off from the rest of the universe. Hawking's ideas, combined with these visual tools, reinforced the real possibility of black holes existing in the cosmos. At the same time, the quality of astronomical observations improved dramatically. Satellites began to launch telescopes beyond Earth's atmosphere, allowing exploration across various wavelengths, including X-rays. This innovation led to a significant discovery, Cygnus X1, a bright, compact source of X-rays that pointed to the existence of a black hole. The intense X-rays were emitted as matter fell into the black hole, accelerating to high speeds due to its gravitational pull. Since the 1970s, the discovery of black holes has proliferated, with potentially hundreds of millions existing in the Milky Way alone. The 2015 detection of gravitational waves from colliding black holes marked a new milestone in astrophysics, underscoring the relevance of black hole research. Yet, theoretical exploration continued to captivate the minds of scientists, presenting black holes as the ultimate enigma. The solutions to Einstein's equations, though elegant, were challenging to uncover. The first, the Schwarzschild solution in 1915, described an uncharged, spherically symmetric black hole. A significant advancement came with the Reisner-Nordström solution, which incorporated electric charge. Nearly 50 years later, the Kerr solution, proposed by Roy Kerr, described a black hole with angular momentum or spin. Imagine a supermassive ballerina spinning rapidly with arms extended. If she pulls her arms in, her rotational speed increases, and when she crosses a certain density threshold, she collapses into a black hole. The angular momentum she possessed before collapse is preserved, as seen in the Kerr solution. Why were there so few black hole solutions? The black hole uniqueness theorem provided the answer. Unlike most astronomical objects, which vary widely, black holes are characterized by only three properties: mass, electric charge, and angular momentum. John Wheeler famously summarized, "Black holes have no hair," emphasizing the simplicity and uniformity of black holes. Every black hole in the universe can be described with just these three parameters, nothing more. Behind the mask of the horizon, black holes have an almost infinite number of ways they could have formed. Yet their final states can be described by just three numbers: mass, spin, and charge. How can such diversity in creation reduce to so few characteristics? The answer connects to an unexpected field of physics: thermodynamics, the study of heat, temperature, and entropy. Consider the air in a room. We perceive it as warm or cold and sense changes in pressure, like the cabin pressure on a descending airplane, but we don't feel individual air molecules. In any given volume of gas, an extremely large, finite number of molecules move in countless directions and speeds. While we can't resolve these individual atoms, we can describe the gas as having a temperature and pressure. These properties represent collective states that emerge from the motion of the atoms. This concept can be described by a quantity called entropy, which counts the number of possible internal configurations a system can have while maintaining its overall properties. The entropy of a gas depends on its bulk properties, temperature and pressure. The higher the temperature, the greater the number of possible arrangements of molecules. Entropy measures this multiplicity of configurations, with higher temperatures allowing more possible microstates. Could these ideas of thermodynamics apply to black holes, the most enigmatic objects in physics? Surprisingly, the answer is yes. Despite there being no atoms or molecules inside black holes, thermodynamic principles still hold. Black holes can have temperature and entropy, a notion first proposed by Jakob Bekenstein and later expanded by Stephen Hawking in the early 1970s. Bekenstein speculated that the black hole itself must have entropy to preserve the second law. He proposed that if a cup of tea entered a black hole, the black hole's entropy would increase by an amount equal to the entropy of the tea. This groundbreaking idea led to the concept of black hole entropy, now known as the Bekenstein-Hawking entropy. The discovery that black holes have entropy is profound, but raises more questions. How does temperature relate to black holes? Astrophysical black holes discovered since the 1960s vary widely in mass. The heaviest known black holes, like Phoenix A or TUN 618, are around 100 billion times the mass of the Sun and are found at the centers of active galaxies, powering enormous quasars. The lightest known black holes are just a few times more massive than the Sun and can be found as companions to stars or pulsars such as PSR J05144002e or the red giant V723. Intriguingly, these smaller black holes are much hotter than their supermassive counterparts, despite being far less massive. Even though their temperatures are minuscule, only 100 millionth of a degree above absolute zero, the concept of heat in black holes still exists. The question remains, where does this heat come from? For, as he thought about it in more detail, Hawking's remarkable mind latched onto a problem with this picture. Imagine a hot gas falling into a black hole and being entirely absorbed. The resulting black hole, it was thought, should be cold, dark, and compact. Nothing could come out. It seemed to be a zero-temperature object. In every other part of physics, when hot and cold objects are mixed, the temperature of the cold object is increased by the mixing. Yet here, the black hole seemed to remain inert, with a temperature of absolute zero. Indeed, this was the whole idea of a black hole. Not even light could escape. But this was where Hawking came in with a striking and surprising idea. Doubling down on the notion of black holes as thermodynamic objects with an entropy, he proposed that black holes also have a temperature. Not a mathematical analogy to temperature, not a gravitational equivalent to temperature, but an ordinary temperature with exactly the same meaning as that we use to talk about ovens, boiling water, and the weather. The most exotic objects in the universe suddenly became eerily familiar. The classical laws of thermodynamics, dating back to the 19th century, relate entropy to temperature. In particular, they say that the temperature of an object is the inverse of the rate of change of its entropy with energy. For a gas, when extra energy is injected, the number of gas configurations increases. By calculating this precisely, we can work out the temperature of the gas. For a black hole, the entropy is actually set by the area of the horizon. In the simplest case of the Schwarzschild solution, this entropy behaves as the square of the mass energy of the black hole. Plugging this relation into the classical 19th century thermodynamic expression for temperature gives a striking result. The black hole must have a temperature, and this temperature changes inversely with the mass energy of the black hole. Big black holes are cold, small black holes are hot. The temperature of a typical astrophysical black hole in our galaxy, formed by a collapsing star and with a mass slightly larger than our Sun, is around 1/1000th of a degree. However, a much smaller, and hypothetical as far as we know, black hole formed by compressing something like Mount Everest down to a point would have a temperature of hundreds of billions of degrees, vastly hotter than the center of each of the largest stars. This unusual property means black holes behave in a way opposite to our intuitions. A normal fire starts off warm and hot. As it gives off heat, it cools, and eventually there is little more than a small glow from the ashes, which eventually dies away to nothing. Black holes, on the other hand, become hotter as they give off heat. While the black hole starts cold, it gets hotter as it loses energy, eventually evaporating in a blaze of radiation. Strange, but characteristic of black holes. As we begin to unravel this, let's start with the simplest question. Why do black holes have a temperature? Hot objects radiate. Place your hand near a fire or an oven, and you will feel the heat without ever touching it. Indeed, precisely what it means for something to be hot is that it transfers heat to something that is cold. Place the two objects next to each other, and they equilibrate at an intermediate temperature as heat goes from the hot body to the cold body. But black holes, we thought, were not meant to give out anything. Were they not introduced as voids in space which may eat and swallow and gobble, dragging all they consume towards some unknown singularity, but do not spit anything out? This, after all, is what the black in black hole refers to. They absorb light but do not emit. And yet, with the revelation they had entropy, this was found to be not quite true. If we could place our hand close to a black hole with a temperature of 1000 degrees, the experience ought to be identical to placing our hand close to an oven with a temperature of 1000 degrees. Just as our hand feels the photons from the oven striking our skin and transferring energy to the skin cells, which is then communicated to our brain via nerve impulses, so too our hand must feel photons from the black hole striking the skin and transferring heat to it. But where would these photons come from? For this to be true, there must be actual particles coming out of the black hole, not simply falling into it. In the 1970s, this seemed absurd, completely inconsistent with the whole idea of what a black hole actually was. And so, could there really be particles coming out of a black hole? Remarkably, the answer is yes. Of Stephen Hawking's many contributions to physics, this result is the most important and the most enduring. The light that emerges from a black hole is called Hawking radiation, and it emerges with precisely the spectrum you would expect, given the temperature of the black hole. Hawking radiation is theoretically well established and has been derived using many different approaches. But what all the approaches have in common is that they sit at the intersection of the physics of gravity, black holes and quantum mechanics. And to understand this, we have to begin by thinking about Heisenberg's uncertainty principle, the idea that there is never a perfectly still vacuum in quantum mechanics. Nothing can be settled down completely. Imagine yourself close to, but just outside, the horizon of a black hole. If you were to cross this horizon, you would fall into the black hole and your fate would be sealed irrevocably. But instead, suppose you have a rocket with enormously powerful engines which are strong enough, just strong enough, to prevent you from falling into the black hole. The engines fire constantly, and you remain outside, just outside the horizon. Imagine two beacons on the rocket, one on the side towards the black hole horizon and one on the side away from it. Light emitted from the horizon side beacon immediately crosses the horizon and falls, never to return, into the black hole singularity. Light emitted from the other beacon, however, pointed away from the black hole, succeeds in escaping the black hole and reaching deep space far away from it. This is similar to how Hawking radiation works. Contained within Heisenberg's uncertainty principle is the idea that in quantum mechanics, even the coldest and emptiest vacuum is not empty. There is an intrinsic energy associated with this vacuum, and it is even possible to borrow energy from the vacuum for a short period of time. The more energy you want to borrow, the shorter the time period you are allowed to borrow it for. This means that for very short periods of time, the vacuum can borrow sufficient energy to create, albeit temporarily particle-antiparticle pairs. Provided these are rapidly reabsorbed again back into the vacuum, and their energy returned to the vacuum, no harm is done to the laws of physics and the law of conservation of energy. Although this may seem strange, this is one of the examples of the complexity of the vacuum in quantum mechanics. Nothing is far from straightforward. Sitting on top of this is the fact this vacuum is not just one of empty space extending in all directions. Here we are considering space just outside the horizon of the black hole, with the gravitational pull of the black hole always ready to take objects through the horizon. This vacuum comes with a direction inwards attached. What happens then, just outside the horizon, when energy is borrowed from the vacuum to create particle-antiparticle pairs, or for particles like the photon, which is its own antiparticle, a pair of two back-to-back photons? Well, for a small instant of time, one can borrow energy to create a pair of photons. For that same incredibly short instant, these particles can travel, and during this incredibly short instant, one of the pair crosses the horizon, the one-way portal towards the singularity. And so the pair can no longer come back together. Just as our rocket, teetering on the edge of the abyss, fires photons both into and out of the black hole, so in a sense does the quantum vacuum. While one particle escapes off to infinity, the other falls into the black hole, and the borrowed vacuum energy now has to be repaid by the black hole. The net result is that one photon escapes, taking a tiny bit of energy with it, and this energy is repaid by the black hole losing a tiny bit of its mass energy. Detailed calculation confirmed Hawking's intuition that this process looks like a hot oven radiating light. The spectrum of photons emitted by the black hole is exactly that of a hot oven with a temperature given by Hawking's formula. And so there it was. Stephen Hawking found that black holes were not black. But that was not the end. As ever with black holes, solving one problem introduced another. Because if you wait long enough, the black hole would eventually evaporate away entirely. There would be no interior of the black hole anymore. We can imagine a history that starts before the black hole is formed, with countless encyclopedias and databases falling in under gravity to create the black hole. Over time, the black hole evaporates, and at the end, there is a gas of particles heading out from where the black hole once was. And so, what has happened to all the information that was once there? According to Hawking's calculation, the emitted radiation was that of a perfectly featureless thermal spectrum, which contained no trace of the original information. Where had it all gone? Could the information be reconstructed from the details of the emitted radiation? For 2 decades, this question was debated. In ordinary quantum mechanics, information is not lost. Were black holes like this? Or did the unusual combination of gravity and quantum mechanics lead to some fundamental differences? Eventually, the answer came from an unexpected direction. The fact that the entropy was proportional to the area, not the volume of the black hole. This was the first sign of a deep and subtle idea called the holographic principle, with huge consequences for the universe as we understood it. Imagine you have dropped a book into a black hole. How you do this, somehow withstanding the brutal accretion disk and waves of radiation, is unimportant. The key thing is somehow you do. We can imagine the book falling until it reaches the central gravitational singularity at the very heart of the black hole, where any information that it carries is crushed utterly. And so, to understand whether or not the information is destroyed or survives, it seems we would need to understand this central singularity. What is the interior of a black hole like? Does information survive in a theory of quantum gravity? If we recorded the details of every photon emitted from the black hole through Hawking radiation, would we, in principle, be able to reconstruct the information? Most of the ideas we have discussed so far, the existence and entropy of black holes as well as Hawking radiation are, however exciting, still ideas which had been mostly worked out by the end of the 1970s. But over the following years, physicists have realized that the physics of black holes contains even more, the first hints of even deeper and stranger truths. In particular, the physics of black holes has given us the first hints of one of the most remarkable and shocking properties of gravity, the holographic principle. And it is this holographic principle that offers the best framework to think about what happens to the information lost to a black hole. To begin with, let's return to Hawking's formula for the entropy of a black hole. There is part of this which may not appear unusual, but is in fact the first indication of something groundbreaking. The entropy of a black hole grows with its area and not with its volume. Physicists knew that the mass of a black hole is equivalent to the area of its event horizon, the geometric area of the surrounding spherically symmetric shell inside which nothing can escape. For the simplest Schwarzschild black hole, this horizon area depends simply on the mass of the black hole. But for spinning black holes, the expression for the horizon area was more complex and depended on both the mass and spin rate of the black hole. But by 1971, it was Stephen Hawking who had shown that whatever happened to a black hole, even including complicated processes which could extract angular momentum from a spinning black hole, actually slowing its spin. This horizon area would only increase. And in the second laws of thermodynamics, it is entropy that can only increase. First Bekenstein and then Hawking realized that it was the horizon area, not the mass or volume or angular momentum of the black hole which behaved in precisely the way that entropy was meant to behave. When objects fall into a black hole, adding to the information and hence entropy inside the black hole, the horizon area of the black hole increases. When two black holes merge, the horizon area of the product black hole is larger than that of either of its components. In complicated slingshots, which can extract both mass and angular momentum from a black hole, the black hole mass decreases, but the horizon area increases. But why is this surprising? Black holes, as we have seen, are similar to gases in some respects. They are both thermodynamic objects with temperatures and entropies. Like hot gases, hot black holes give off radiation. However, there is an important and subtle way in which they are different. The entropy of any object is a measure of the total number of internal configurations that an object can have, a measure of the number of ways of rearranging the innards while keeping the external properties the same. For a gas, the entropy grows with the volume of the gas. If you imagine a balloon at a certain pressure and we hold the pressure the same, the bigger the volume of the balloon, the more the number of possible allowed internal configurations of the gas. Suppose we divide up the entire volume of the gas into lots of little blocks, little unit volumes of space. Each of these volumes could be either off, perhaps off means it is not. This is a very simple way of thinking about a gas, but it gives us a key to understand the physics of entropy. How many total configurations are there? Each block can be on or off, so there are two choices for each block. With one block, there would be two choices. For two blocks, there would be 2 times 2 equals 4 choices. For 3 blocks, 2 times 2 times 2 equals 8 choices. For 100 blocks, we multiply 2 by 100 times. Generally, the number of total configurations is 2, raised to the power of the number of blocks. And so what is different about black holes? For black holes, the Bekenstein-Hawking entropy depends on the area of the black hole horizon and not on the volume. In terms of our picture of little blocks, each of which can either be a 1 or a 0, what this formula implies is that for black holes, we can count the number of internal configurations by splitting the horizon area into many small little blocks, each of which is either 1 or off, a 1 or a 0. The counting looks similar to what we did for gases, but only provided we do the counting on the horizon of the black hole and not on the interior volume of the black hole. And so, the holographic principle is the statement that, for many gravitational systems, the physics of the system is entirely encoded in the boundary of the system. The equations for gravity in the interior can be rewritten or translated into a different set of equations, which describes a non-gravitational theory that lives only on this boundary. Gravitational systems in a three-dimensional space can be equivalent to non-gravitational systems on the two-dimensional boundary. Gravitational systems in a five-dimensional space can be equivalent to non-gravitational systems on the four-dimensional boundary. Gravitational systems that live in a certain amount of dimensions are equivalent to those that live in one less. One of the dimensions in the gravitational theory turns out to be redundant. This idea, also called today the ADS-CFT correspondence, is one of the deepest ideas in modern theoretical physics, and it is supported by a vast number of calculations. The key claim is that two separate mathematical theories, a gravitational theory in, say, 5 dimensions, and a non-gravitational quantum theory in 4 dimensions, are actually identical theories, just written in very different language. This has been mooted as a way to link the previously incompatible gravity and quantum mechanics, the holy grail of modern physics. And it was the Bekenstein-Hawking expression for the entropy of the black hole that represented the first inkling of this theory. But how does holography help with the information paradox? Where has all the information gone? Holography tells us that a gravitational system and its evolution can be described through an alternative, non-gravitational language. Suppose a gravitational system with an alternative non-gravitational holographic description has a black hole which forms and evaporates. In the context of the gravitational theory, we would worry about whether the information is lost. But in the alternative holographic lower dimensional description, the process of formation and evaporation of the black hole occurs in a completely non-gravitational language. Here, it is simply an ordinary quantum mechanical system evolving in an ordinary quantum mechanical fashion. And there are no problems involving singularities or horizons. In such an ordinary quantum system, there is no question of information loss. The information is simply kept on the horizon, stored on a lower dimensional boundary. But still, even if we know the information will be preserved, where is it exactly? The best answer yet is that it will lie in the details of the Hawking radiation. Although we may think of the radiation as being emitted from the black hole like an oven, all uncorrelated with each other, this is not quite correct. Instead, physicists believe that all the emitted photons are subtly correlated and entangled with each other, and it is here that lies the details of the information that fell into the black hole.